Hey, this is Jen, and you really do love science. You just don't know it yet. Let's talk now about the difference between accuracy and precision. I'm sure you've heard people say, oh, she's being so accurate, or oh, she's being so precise. And maybe until now you've never known the difference between being accurate and being precise. So let's talk about it. Accuracy tells how close your measurement is to the correct or the accepted value. So let's write down this definition that accuracy is closeness to a correct or an accepted value, and the accepted value must be known for you to report on your accuracy. For example, let's say you were doing a lab in your class and you had to measure the mass of a certain metal and then the volume of a certain metal, and you were trying to take mass divided by volume to get the density of the metal. Well, you can't report on the accuracy of your density calculations unless your teacher tells you what the accepted value or the known value is for the density of that metal. And then you can make the comparison and you can say, hey, our measurement was accurate, or our measurement was not so accurate. So it's really about being right or wrong. That's accuracy. Precision is a little bit different. Precision I like to call repeatability. Is that a word? Repeatability or consistency in your measurements. Have you ever had a bathroom scale that's like 5 pounds off, and it's really, really consistent? I mean, it's always 5 pounds off. It's not accurate, but at least it's consistent. Well, that scale, that bathroom scale, is precise because its measurements are consistent. Now, you can have good precision and good accuracy, which is ideal, or you can have good precision with poor accuracy. And think about it. If your measurements are consistent and they're not all over the place, then you're probably doing a good job in being careful in your lab. So let's draw some dartboards, even though I'm not very good at drawing these circles. But let's say we have some target practice here with some darts. This is a great visual way to understand the difference between accuracy and precision. I'm going to make my darts, I don't know, bright pink or red. Okay, all you need is one dart to show good accuracy. Bam. There's the dart. We hit the bullseye. That is good accuracy right there. Precision is repeatability, and so you could have good precision by having your darts all land sort of in the same spot without hitting the bullseye, without being in the spot you wanted. So here we have good precision. Sorry for writing on top of the dart, but this one is poor accuracy. Now, I don't want to lead you to believe that good precision is always poor accuracy, so I drew a third dartboard where we have good precision, good repeatability, and good accuracy. So this is good precision because they were consistent, and this is also good accuracy. Let's draw one with poor precision. Here's one dart, here's another dart, and here's another dart. So this is poor precision, and this is also poor accuracy. You never really hit the bullseye. So in your measurements, if your measurements are correct and you're actually getting the right answer, you can say, oh, that's very accurate. But if you're consistent, then you can say you're precise. And you could be consistent and correct, or you could be consistent and incorrect. I think you understand the difference now between accuracy and precision. How do we actually report it? In your lab report, you're not going to be drawing dartboards before you hand in your lab. So there's a different way to report your accuracy and your precision when you're doing a lab report. Let's talk about that. So accuracy is reported using something called percent error. And percent error is like a measurement of percentage-wise how far off were you from the accepted value. So what you're going to do is you're going to get the difference between your measurement and the accepted value. I am going to run out of room. So let's say accepted value minus my measurement, and we're going to take the absolute value of that because we just want to get the difference. We don't want the difference to be a negative number. We don't want to get a negative percent error. So we make sure we get the absolute value of that difference, and then we're going to divide that by the accepted value. So it's kind of like saying, how far off was I divided by the right answer? Multiply by 100%, and you're going to get your percent error. So it's, again, like saying, in terms of percent, how far off was I compared to the accepted value? I'll give you an example, really easy example. Let's say the length of a table is, the accepted value is 2.00 meters, and your measurement was 2.31 meters. Well, your percent error would simply be 2.00 minus 2.31, absolute value, because we don't want to get a negative percent error, divided by the accepted value, times 100%, and we should get our percent that way. So you end up with 15.5% error, and you go ahead and you write the word error after the symbol for percent. So 15.5% error in a lab is actually not very good. You want to try to be under 10% error to feel good about your lab results. So you see how percent error kind of shows how far off you were from the accepted value? Well, now what we're going to do is how to report precision results. So precision is reported using something called percent deviation. Percent deviation is like saying, hey, how far off was each of my measurements from the average of all of my measurements? So for percent deviation, you're going to have more than one measurement. So let's say you're measuring something like how long it takes for something to fall. Well, when you do 3 trials, you've got your stopwatch there, and you drop the object and you hit the stopwatch and you get the time. Well, you could do the experiment 3 times and you could hit the stopwatch 3 times and you can get 3 different answers. Those are 3 different measurements. What you're going to do is you're going to get the average of all those measurements, and then you're going to compare each one of your measurements to the average. I'll give you an example in just a minute. Notice the absolute value signs on each side of this equation that I wrote, because you don't want to, again, get a negative percent when you calculate percent deviation. So you get the difference between the average measurement and each measurement, and then you divide that by the average of all the measurements times 100. It's really hard to understand it when it's in an equation form like this, so I think we should do an example. So let's say you are measuring how long it takes for something to fall, and you have like trial 1 and trial 2 and trial 3. Okay, you drop the object, and in trial 1 it took 0.86 seconds to fall, and in trial 2 it took 0.92 seconds to fall, and in trial 3 it took 0.94 seconds to fall. And it was just a matter of how quickly your hand could make the stopwatch start and stop. You got 3 different measurements, but it was the same exact object falling from the same exact distance. So what you're going to do is you're going to get that average. In order to do percent deviation, which is a report on precision, you need to get your average measurement, or in this case, it's your average time. And this is very messy. On your lab report, you would not make it this messy, believe me. But here we go. We get 0.86 and 0.92 and 0.94. And we add those all up and we divide by 3. And we get an average of 0.90666. There's our average. Now, we have to do precision for each trial. So for trial 1, the percent deviation, meaning how far off was it from your average measurement, it's going to be the difference between 0.86 and the average, which is 0.90667. And it doesn't matter which one you put first. I could have done 0.90667 minus 0.86. It doesn't matter, because when you do absolute value, the difference between those two is the same. I'm going to do this absolute value sign in red so it doesn't look like a 1. Okay? So there we have the difference between those two, and we're going to divide them by the number that is the average. then we're going to multiply by 100%. So the difference, and this is just for trial 1, and you're going to get a percent deviation for each trial. It's like for each trial, how far off was that from the average? So I'm going to say 0.86 minus 0.906667, and we get absolute value 0.046667. And then I'm going to divide that by the average, 0.906667 or something like that, and times 100. So my percent deviation for trial 1 was 5.147, and I'll look at these significant digits. I see that I've got 2 significant figures in all of my measurements, so I'm going to go ahead and call this 5.1%. So I'm going to say 5.1% deviation, and that was for trial 1. Now again, you're going to do percent deviation for each trial, but can you see how this is a report of how far off each measurement was from the average measurement, and that is a good report on your consistency, or how consistent your results were. And so I hope that this helps you understand accuracy and precision a little bit more. And before we go, I'm just going to add one final definition here. I don't know if I can pick the same color that I was using, but the repeatability or consistency is a pretty cryptic definition for precision. So I'm just going to add a definition and say that precision is also how close the measurements are to each other. Not necessarily to the accepted value, or to the right answer, but how close the measurements are to each other. So hopefully you understand accuracy and precision a little bit better, and I hope you do well on your next quiz or test.